Hello, and welcome to Lesson 10. Today we are going to start our investigation into some of the more common math models, starting with dynamical systems. So first of all, what is a dynamical system? So, a dynamical system is a really common model that is used to simulate the change of quantities over time. We normally express dynamical systems as equations showing the rate of change. And this leads us to two different types of dynamical systems, the discrete dynamical system and the continuous dynamical system. The discrete dynamical system have time that only takes on certain values, normally integers, for example, day 1, day 2, day 3. And we normally represent discrete dynamical systems using difference equations. However, on the other hand, a continuous dynamical system have time that takes on a spectrum of continuous values, as its name suggests, and we normally use differential equations, which is derived from calculus, to model continuous dynamical systems. Now, let's look at an example of a discrete dynamical system. So we have a car rental company in two locations, New York and Philadelphia. In the morning, customers rent cars at both locations and return the same afternoon. This means that we can treat it as a discrete system because the change in the number of cars the rental company have in each of its two branches only occurs in the unit of days. And we have these rates. Every day, 80% of the cars in New York are rented, half returned in Philadelphia, half in New York. Similarly, 60% of the cars in Philadelphia are rented, with 70% returned in New York, of course the other 30% back in Philadelphia. So, we can draw a simple diagram showing this relationship. So, N is the number of cars in New York, and P is the number of cars in Philadelphia. And we can see that every day, 40% of the cars in New York go to Philadelphia, 42% of the cars in Philadelphia go to New York, and we can also see that some of the cars, they left New York and came back to New York. And some of the cars left Philadelphia and came back. And we don't really need to care about these two parts because they do not lead to a change in the number of cars in New York or Philadelphia. And thus, we can write our discrete dynamical system. And that is our difference equations. It looks like this. So, we use delta because it's discrete, and it represents the change of the cars in New York over time equals to negative 40% times the number of cars in New York because these many cars leave, plus 42% of the number of cars in Philadelphia. And the change of the number of cars in Philadelphia is negative 42% of the number of cars in Philadelphia, which is leaving, plus 40% of the cars in New York, which came in. And we can realize that if we add these two different equations, it will result in the change in the number of cars in New York plus the change in number of cars in Philadelphia in a certain day is 0 because we do not have new cars entering the system. Now let's check out a continuous dynamical system. So we have two interconnected lakes, A and B, and every day 5% of the water from A goes to B, and a pump pumps 1,000 cubic meters back, and every day water goes into A at a rate of 10% of its volume per day, and water flows into B at 1,200 cubic meters per day. And there's also water draining out from both lakes. And thus we can draw a similar diagram as the one we had in the previous example. And that is, we have A and B, and we show the relationships and the rates, modeling how much water comes into A and leaves A and comes into B and leaves B every day. And from this, we can write a dynamical system. Because we are aware that water is constantly flowing, we will want to use a continuous system, and that is differential equations. Here, contrary to the previous example, we use dA over dt instead of delta A over delta t to show the continuous nature. And here we write these differential equations. However, if you notice, you'll notice that if we sum up these two equations, the total rate in which water volume of the both lakes change is not 0 because water is entering and leaving the system. As a dynamical system is a simulation model, we would often want to know how to simulate it. So before we start simulation, we need to determine the initial condition because each change in quantity has to have an initial condition or a value before any change. For example, A and B in our previous example about the lakes, they have an initial volume. And for discrete systems, we find the rate of change in an interval and then use that rate of change to find the values for the next interval, then repeat. For example, in our example about the cars in New York and Philadelphia, we can first, on day 1, find the number of cars in New York that will go to Philadelphia, and the number of Philadelphia cars that will go back to New York. And we use that number to find the number of cars in both cities on the second day. And then we repeat and go on and on and on to see how the number of cars ultimately change. However, for a continuous system, we will use Euler's method. Actually, Euler's method, it might seem complicated, but it is just treating a continuous system as a discrete system. So, we have here the formula for Euler's method. It's really simple, so you essentially pick a time interval and you assume that the rate of change is fixed in that time interval, and you use that rate of change to approximate how the system will grow. And a smaller value of A, or the time interval, it will provide a closer approximation. So sometimes we want a smaller value of A. And we will also like to know some common tools for simulating. We can either program our own programs, or if you are not familiar with programming, spreadsheets will do the work good enough. Now finally, let's look at how we analyze and present our dynamical systems. The most important form of analysis for dynamical systems is sensitivity analysis. And in sensitivity analysis, we may want to analyze the initial conditions, and we also want to analyze the important rates of changes. For example, if something influences this rate in what way, we might want to analyze how this rate's change will influence the result of our dynamical system. However, we do not perform sensitivity analysis on things that are relatively fixed. For example, we never do a sensitivity analysis on pi, because the value of pi is always 3.14 on without any doubt. Now, how do we present? So we can show the relationship between quantities and the rates using diagrams, as I have done in my two examples. And we also want equations showing the difference or differential equations, since they are the meat of your dynamical systems. Finally, to show the results, you use line plots because it's something that changes with time. And that's what I have to talk about dynamical systems. And thank you for listening. I hope you enjoyed it.